Καλησπέρα σας. Σας ευχαριστούμε που ήρθατε απόψε στην αίθουσα εκδηλώσεων Τεχνικού Επιμελητηρίου της Ελλάδος για την ομιλία του καθηγητή του κ. Arvin Farid. Είναι τιμή μας που τον έχουμε μαζί μας. Πρόκειται για μια συνδιοργάνωση της Ελληνικής Επιστημονικής Εταιρείας Εδαφομηχανικής και Γεωτεχνικής Μηχανικής και του τομέα Γεωτεχνικής Μηχανικής του Εθνικού Μεσοβίου Πολυτεχνείου. Και χωρίς άλλη καθυστέρηση, καλώ στο βήμα την κυρία Μαρίνα Πανταζίδου για να προσφωνήσει τον ομιλητή μας στα αγγλικά.
We are lucky to have Professor Farid with us. We are lucky because next week is the 9th International Conference of Environmental Geotechnics, and he agreed to give us this lecture on the way to Crete. Professor Arvin Farid is at Boise State, which is in Idaho, and he is the chair of the Environmental Engineering Technical Committee of the GeoInstitute. So the GeoInstitute is the equivalent of the Hellenic Society of soil mechanics and geotechnical engineering. And he's also an editor of the journal Environmental Geotechnics. So heavily in environmental geotechnics, many committees. I will skip the degrees. And he will talk us today about his research with, I call the area geophysics. Is this wrong? Or it says here beyond geophysics. So we will learn what is beyond geophysics. Yes. So many applications of electromagnetic waves, both in environmental and geotechnical engineering. So it's a good opportunity to bring the two areas together. So without further ado, I will ask Professor Farid to start his lecture.
Thank you. Thanks. Thank you, Marina. Thank you, Marina. Thanks for the society and the audience. It's an honor and pleasure to be here among you. And hopefully this talk is something that would excite you about thinking outside the box type of approach to problems that you may face. A little bit of background about myself. My background is both educational and research backgrounds are in civil and electrical engineering. So, and the civil part is geotechnical, a little bit of structures, and geoenvironmental is mostly what I've been doing in the recent past. And as you know, this is mostly driven by the funding sources that are available in the United States. So I'll start with this, that I put my Geoenvironmental Engineering Technical Committee hat on. Next September, between September 8th to 11th, we'll have the GeoEnviroNet Conference 2024. This is the fifth of the series, equivalent to ISEC, International Conference on Environmental Geotechniques. The ASC, American Society of Civil Engineering equivalent, is this GeoEnviroNet. And it's going to be in beautiful Portland, Oregon. And the theme is quite broad. In my opinion, as I mentioned, geoenvironmental is probably broader than geotechnical in a way. And you could see it's basically resilience and sustainability of the geoenvironment in the face of changing climate. That's what the theme is. These are some of the tracks you could see that are related to everything climate change related and geoenvironmental related, and extreme events and extreme environments, be it permafrost, frozen soil, or wildfire conditions, or nuclear repository, waste repository, and so on and so forth. All of them will be covered in this conference. So quite broad. And now back to the talk. I will divide this talk into two sections. The first one is the traditional geophysics and how electromagnetic waves have been used to detect anomalies within soil or non-destructively test the structures or characterize material. And then we'll talk about what our team sort of pioneered in terms of how electromagnetic waves could be used for other purposes. Think of it as a two-way street. Everybody thought about how the medium of interest impacted electromagnetic waves. And that's geophysics. And the next step is how we can use electromagnetic waves to alter the medium. So in terms of the traditional geophysics, what it is basically you try to discriminate electric property contrast. And it could be done in time domain and frequency domain. And I'll cover all of these things briefly in terms of the inversion and the forward models and the inverse models and the imaging. So the way it's done is if you have typical geophysics is done in two modes. The surface reflection, an example is ground penetrating radar, where you have a transmitter above the surface, you send the waves into the ground, and when you hit a contrast where two media have a contrast in electric or magnetic properties, the waves bounce back or reflect or scatter. And looking at that reflection, you could figure out what is there. Another mode is basically cross-borehole radar, when you have a transmitter in one hole and then receivers in others, and you send the waves, and if there's an anomaly, in this case, let's say DNAPL contamination, dense non-aqueous phase liquids, in there, they would scatter the waves. So when you have the receiver in other boreholes, you could figure out what is hidden there. And how does it work? Waves propagate, and their propagation is a function of the electrical and magnetic properties of the medium. So if there's a change in the properties of the medium, the waves would be impacted, and it would show up in the results. And people have tried, geophysicists have tried to use this to characterize material as well, find anomalies in there, find basically moisture of soil, density of the soil, and a lot of other properties like salinity and so on and so forth. And obviously we have electric properties and magnetic properties. And among electric properties, you have electric conductivity that most of you are familiar with. That's what you use with your cables and cords and power. And we have dielectric permittivity. And dielectric permittivity is a complex variable, meaning it has a real part and imaginary part. Typically, we use epsilon for that. And the asterisk means it's complex. The epsilon prime is the real, and epsilon double prime is the imaginary part. Typically, we normalize this to the dielectric permittivity of vacuum or air or free space, which is epsilon 0, 8.8520 times 10, and so on and so forth. That's basically, you normalize this to a number, and when you normalize epsilon asterisk to epsilon 0, you call it kappa, which is a Latin, again, alphabet or Greek alphabet, I should say. And this is the relative dielectric permittivity, which has its own real and imaginary part. The real part, which is kappa prime, is basically known as dielectric constant. That's the one controls the storage and propagation and polarization. And we'll talk about polarization later on. And kappa double prime is related to the damping and conductive loss and loss of energy and electromagnetic energy turning into heat, basically. And as long as there's a contrast between kappa prime or kappa double prime of your medium and background, your background medium and your anomaly, your object, you could detect them. This is an example. You could see the density of PCE, which is a DNAPL, or water and dry soil, saturated soil, and so on and so forth. And looking at the dielectric constant, kappa prime, you see for water it's almost 80, but for DNAPL it's around 3, 2 point something or 3. And for saturated soil, could be up to 20. For dry soil, it's 6 or 7. So you see there's a contrast, and if there's a contrast, the waves would be scattered and you could detect objects. And the properties change with frequency. They're not constant. And this variation with frequency is called dispersiveness. So these properties are dispersive, meaning they are a function of frequency. And the way things are done by geophysicists is this way. First, you need a forward model. I don't know if inversion and inverse problems is what you have seen, but forward model means what? That means that if I have a signal Gaussian signal or sinusoidal signal or whatever, that I know, a known excitation signal source, and I send it to a medium, which is a known medium. If I have a good forward model, I could simulate how the wave would propagate, and I could figure out and compute and calculate what the received signal would be. That's called the forward model. So the unknown is the received signal. And you could simulate this because we're dealing with waves in time domains. You could simulate them in frequency domains. And the input parameters would be the properties of the known material, known medium for this simulation. And obviously, you could experimentally measure that signal as well, that received signal as well. Now, obviously, any model, any simulation, unless it's validated experimentally, is pretty useless and unreliable. So you need to simulate this. If you're creating this forward model numerical simulation, you need to experimentally measure the received signal and see if they match or not for a known medium. If your simulation matches your experiments, and if that's the case, now you've got a forward model that's validated. The inverse problem is what geophysicists do day in and day out. Basically, they say, I don't know what the medium is. It's unknown. I don't know what's in it, what its density or moisture is, or whether there's a landmine in there or what, or a tunnel. I send a known excitation again, and experimentally or in the field, I measure the received signal. These are the known. Now, if I could invert my forward model, like F was the forward model, F inverse would be the inverse model, then I would be able to figure out what my medium is. But the inversion is difficult because it's not a simple function that you could invert. The inversion typically is run through methods such as optimization schemes, which means, and how would the optimization schemes work? That means you know what the signal is that you're sending, you know what the received signal is experimentally, that's E sub experiment, and then what you do is you assume some properties for your medium, you run your forward model, and you calculate the received signals numerically. And then you compare these two. If they're the same, if the difference is small, and that difference is called the cost function, then you hit the lottery. If the difference is not small, then you change the properties that you assume, and then you calculate your received signal again, you look at the difference, and you continue this loop all the way up until that cost function is minimized. Then you could say my assumptions were perfect. I figured out what my medium is. That, in simple words, is what inversion is, and that's what geophysicists do day in and day out. And they use it basically, and then basically the inverse problem was solved. That's what geophysicists do. Now let me show you a couple of examples. In terms of the forward model, the electromagnetic waves are governed by Maxwell's equations. These are Maxwell's equations. You got to simulate them either in time domain or time, in time domain. You can see I'm tired, I can't talk. Time domain or frequency domain. And it's much more complex than simulating seepage or a structure. So you gotta, because of that sort of relation between electric field and magnetic field, like in this case, we used, for finite difference time domain, we used a Yee cell and modified it. And basically, we assumed that the impedance of the material, the medium, is complex, and the conductivity is complex as a function of the impedance. And we solved those equations. The model was created from scratch in Fortran, actually. Surprisingly, electrical engineers love Fortran more than other languages. And then some of the input parameters that you could use, and we validated the experiment that I'll show you later on. This is an example of this. This is a movie. How can I, if I hit enter, the movie would run? Or so here we have the medium. That rod is a monopole antenna at the center of the soil, and that little blue is DNAPL pool. Now I'm showing a cross section of this, a slice of this medium to you as a video, a 2D slice. The vertical yellow slice is called the depth slice. and the horizontal green slash is called the cross-sectional slash, again, in electrical engineering terms. So I'll show you first the vertical or depth slash. What I'm showing here is just soil, nothing else. And it's a homogeneous soil. So if, oh, no, it's not running that way. The keyboard somewhere that we could click on. Oh, there's a mouse. So if I click on this, you see the waves come down through the antenna and uniformly propagate through the soil. That is called the background or incident field. Now, if in the forward model, if we had the object in there, and now I'm showing you the horizontal cross-section, the object is hidden on the right. And if I hide the object in the model and run the simulation, now you can see that the waves that come out get scattered and skewed on the right side where the object is. That is called the total field. If I have the total field, soil and the object, and I have the background or incident field, just the soil, I can mathematically subtract them, simple subtraction. And if I subtract them, then we get to something called the scatter field, which is the signature of the object. It feels like it's propagating through from the object. That the scattered field, the scattered signature of the object, feels like it's propagating from the object. That's the one we're looking for, scattered field. And if we find that scattered field, we can figure out what we have in that medium. This is in frequency domain, where you don't solve the whole suite of Maxwell's equations. You solve Helmholtz equations. And that K that you see is a function of the dielectric permittivity and the frequency. And basically KB is for the background, KS is for the scattered case, and I don't want to get into the details. And we use the Green's function with the first or second order Born approximation, solve this, and figure out what are a scattered field. That last one, a scattered field, would look like in frequency domain. Frequency domain looks like a snapshot in time. There is no time propagation, it's just one snapshot. So this is a forward model. This is an experimental setup. I don't want to get into how the setup was built, but the measurement in the field could be in time domain. Basically, you measure the signal that is received and how long it travels, or it could be measured in frequency domain. This is called an S measurement, scattering measurement. How does it run? Up there you have an antenna, a transmitter on the left, a receiver on the right. The wave comes off of the transmitter, goes to the receiver. And at the bottom figure is called the top one is called S21, measurement from antenna 1 to 2. The bottom one is called S11, meaning the transmitter is the receiver. So the waves go out, bounce back, and are received at the antenna. And basically what you're measuring is the response. And what is the response? Is the ratio between the received signal and the transmitted signal. And that is usually shown in dB, basically a log scale, decibel. And so you have either S21, which is transmission from 1 to 2, antenna 1 to antenna 2, or S11, which is reflection at antenna 1. So those are the type of measurements we run, but they're in frequency domain. They're not in time domain. So there are ways to convert these in time. And then development of that antenna is an antenna that was basically developed years ago and solves a lot of problems that other monopole antennas have. Can't get into the details of that. But anyway, so in this case, in these measurements, you face a big challenge that us geotechnical engineers a lot of times forget, or geoenvironmentalists forget. And the thing is this: imagine there's a river, and you want to stick a flow meter in there and measure what the flow is. You're messing up the flow right there with your tool, your sensor, your measurement tool. The river is big, that messed up measurement may not be off the actual measurement. But imagine you have a tiny stream and you stick your flow meter there. Your measurement is messed up by the measuring tool. Any measurement that you have experimentally in the world is messed up by the sensor, is skewed by the sensor. And this is basically one of the holy grails of measurement in electrical engineering and geophysics. And we came up with a novel solution that basically used a cascading system. Imagine this is the real experiment. You have an antenna at the end, and another antenna at the other end, and the middle part is the soil. What you're measuring is either S11 or S22 or S21. It's a measurement that is skewed, and it's basically measuring the two antennas and the soil, not the soil alone. If you have interest in undisturbed measurement, here what we did is we assumed this was a cascade of two-port junctions. The antenna was simulated separate, the other antenna, receiver and transmitter, and the soil, and we mathematically figure out what the S21 of the soil alone was. And we call it the channel transfer function. And this is what it's published years ago, but this is a novel way that basically solves access that holy grail. Now we get that measurement that's independent of the sensor. And this method is a black box approach, could be applied to any other measurement. It's a mathematical, I mean, all the engineering boils down to physics, physics boils down to mathematics. So if you know mathematics, you know everything. So this is a mathematical approach to a problem that doesn't have to be this problem. So now another example, and here I'm not showing the actual measurement, but the actual measurement tweaked to a channel transfer function matches the simulation. If I showed you, later on I'll show you the experimental measurement. It doesn't look anything like that dashed line of simulation, but the channel transfer function does look like that. Actually, and the other thing is this was in frequency domain. I can convert it in time domain. Measurement in time domain is not easy, but we can convert measurement in time domain or frequency domain, the previous S measurement, to time domain measurement. How? You assume this is your signal, and your signal that you send out X in this equation would convolve with a medium G and give you the received signal Y. This is a very complex convolution in time domain. If you take this using fast Fourier transform into frequency domain, that convolution turns into a multiplication, meaning the X, the transmitted signal in frequency domain, simply multiplied by the medium G gives you the received signal. Which means in this case, and this is, by the way, the measurement doesn't look anything like the actual measurement, doesn't look anything like the signal, that the simulation that you saw. So what you can do here is you have your X, take it into the frequency domain, you have capital X now. And you have, if you have your Y, take it to frequency domain, you have capital Y, then divide them, you can figure out the G. Or you could do a lot of other work, or you can, if you know the G, you can find what your capital Y is. This is the capital Y from the simulation that you see bottom left. And then you inverse fast Fourier transform that, you get your received signal in time domain. In other words, I sent the signal at 1,000, I believe this is picoseconds, and I figured out that the signal would have been received at around 6,000 picoseconds without even running any time domain measurements. Through Fourier, FFT, and IFFT, I can basically bypass the time domain measurement, which is very difficult, and get the time domain measurement mathematics. So all of these things are what geophysicists do day in and day out. I mean, some of that. And then you could build an image like a tomogram of where the object is, which is that red portion is where the contamination was. Using cross-borehole radar, that could be shown. This is what geophysicists do. They know the electromagnetic waves are impacted by soil, so they look at that scattering and figure out what's in there. Now, what is it that we did? Years ago, I think it was 2008, I thought that, hey, if electromagnetic waves are scattered by the medium, if I crank up the power a little bit, the medium might be scattered by the electromagnetic waves as well. So let's see what happens. Something could happen to the medium as well. So we tried to crank up the power a little and see what happens. So this is the impact of electromagnetic waves on the medium to see what is happening. And think about remediation. The first example is remediation. I mean, this is not the older work. The liquefaction is the newer work ongoing, so I cannot reveal all of the results, but this I can first. So a lot of groundwater in the United States are contaminated, and a lot of that they are contaminated with different things, especially DNAPL or PFAS and a lot of other things. Marina knows what I'm talking about if you're into geoenvironmental engineering. And to remediate those, to clean up, there are different ways. Ex situ method, like you dig the soil, send it to a plant, you burn it, you clean it, you do something, wash it. Or in situ method, like air spotting. I'll show you an air spotting method later on. That you try to inject air or some chemicals in there and clean it up. People use electric, and these ex situ methods are costly. To dig the soil out and clean it up, it's very costly. And there's also natural remediation, like volatilization. Your contaminants have a component that quickly evaporates if it's exposed to air. Those are called volatile organic compounds for these cases. And they vaporize if they're exposed to air. And there are microbes in soil that can biodegrade, can break down your contaminants as well. That's called biodegradation. These are all slow. If we could stimulate them, we could clean up the soil, not in 1,000 years or 100 years, but in a year or so. So, and air spotting is one method. People pump air into the soil and basically vaporize the contaminants, the VOC part, and then the rest, they can inject microbes in there or food for microbes and hope that the microbes would break down contaminants. That's called bioremediation. And we'll talk about the air spotting later on. And a lot of these methods are basically used, but to stimulate them, people use DC current, direct current. And the whole field of electrokinetics comes from that. And people have tried to use AC currents, alternating currents, like the one we have in these outlets for remediation as well. The problem with AC and DC is they generate a lot of heat. The other problem with DC is it alters the pH of the medium. They're all both bad for the very microbes you're trying to use and stimulate for biodegradation. So we thought this is an issue. Let's come up with a better way. And with electric current, you just have a resistance of the medium or resistivity. You put a voltage, you get a current, no more control, period. With electromagnetic waves, you have so many different parameters that you could control. And I'll explain what we thought. This is what we thought. And this is the need of, or where the idea came to my mind. The vertical axis shows epsilon or kappa prime and kappa double prime. Remember, dialectic, the real and imaginary. The horizontal axis is the frequency. When you have a wave, what time did we start? When we have an electric field that's constant, meaning positive here, negative there, anything that is charged would orient itself. Like if it's an ion that's negative, would go to the positive pole, and the positive would go to the negative. If you have a molecule that's a dipole, like the water, it would tilt and the negative would face one way and positive would face the other way. Because if you remember, some material are charged, like ions, either positive or negative. Some materials are the molecules are neutral. They're uncharged, there's no charge. But even among the neutral materials, you have molecules like methane, CH4, where the positive and negatives are canceling each other, but they're uniformly distributed around. So they're not only neutral, they're non-polar. They don't have a pole. But if you look at the water molecule, it's neutral. 2 positive hydrogens and oxygen with 2 negatives. It's neutral, but the positives are on one end, negatives are on the other end. Which means it's a dipole. It has 2 poles. If I put water in an electric field, it would orient itself. Now, if I have an alternating electric field, the field keeps flip-flopping, positive, negative, keep flip-flopping at a frequency of, let's say, 100 megahertz. And these water molecules keep flip-flop, oscillating left, back, forth, back. And that's how the molecule would start absorbing energy. That's why you could put your coffee in the microwave and heat it up. The more water in your material, the faster energy is absorbed. And how much energy is absorbed in there is related to how many oscillations it takes, which is related to kappa prime, the real oscillation. So that's why if you put a dry piece of wood in your microwave, you're not going to heat it up. You need some water to heat it up. Now, if you look at this, when I have a field that's only flip-flopping at a low speed, everything, small, big, electrons, atoms, molecules, bound water, free water is oscillating. That's why on the left side, epsilon prime and epsilon is pretty high, because everything is oscillating. The higher the epsilon prime, that means everything is oscillating in the field. Now, if the frequency goes up and up and up, gets to around 10, 30, 20 megahertz, bound water stops oscillating. Now, free water and everything else is oscillating. Meaning bound water relaxes and epsilon drops down. If I go, epsilon prime drops down. If I go to a higher frequency, now heavier stuff, like even free water molecules and heavy molecules stop oscillating. That's why your epsilon prime drops down in the case. And then you go higher and water is not absorbing energy anymore. That's higher frequency. You go even higher, atoms will stop oscillating. You go even higher, electrons will stop oscillating. You go to X-ray, nothing oscillates, nothing absorbs energy, which is why X-ray goes through your body. Now you go, but microwave or visible light doesn't. So that's why you take an X-ray. So these relaxation mechanisms, there are different relaxation mechanisms. And if I pick the right frequency, I can decide what I want to oscillate and what I don't. And I can decide how much energy would be absorbed. And I could control things so that things don't heat up, but I can move them. And when I thought of this, I thought, okay, the least I could do is I could stimulate diffusion of material. And if I have a chemical that's trapped, I can move it. I can help the same natural process speed up. That's what I hope. Then we realized that we opened the can of worms, but we found so many other things that happen in there. And I'll show you a couple of them. So all these experiments were done in the lab, so we had to do it within a cavity, meaning we had to trap everything within a box or middle, so it wouldn't impact your body. There's no danger from electromagnetic waves at these frequencies. Anyways, at low frequency, somebody says your cell phone gives you cancer, but they don't know what they're talking about. So yes, your cell phone can heat up your brain and cook your brain, but the battery cooks it more than the waves do anyways. Not at these frequencies and powers. Electromagnetic waves are non-ionizing waves at low frequencies and these powers. Hence, there's no danger to them, no danger of ionization or cancer and so on and so forth. Yes, X-ray, gamma rays, we're talking about cancer because of that high frequency. Electrons are released and photons are released and so on. Or gamma and so on and so on. But we did it within a cavity, and cavities, the only difference is now you don't have traveling wave patterns. You have standing wave patterns. And you could create different wave patterns depending on what the frequency is and what the wavelength of that sinusoidal wavelength is with respect to the size of that box. You could create first mode, second mode, third mode. Think of it as modes of vibration of the building. So we created this box. It's made of plexiglass, but the faces are covered with a film that's the metal that you see through. Transparent, electrically conductive films. So this is a cavity, and up left there's a little loop antenna that magnetically sights the medium. And what we thought, okay, we put a little cup at the center, right here, and we will inject chemicals in there that simulate DNFL to see what happens. We hope that it would diffuse faster. And then we move the cup around to see what happens in different locations. So these are all the tools we have. I don't want to get into the details of these with signal generators and amplifiers and a spectrum analyzer and so on and so forth. And this is the loop antenna we have. to excite the medium on the left, and the monopole antenna is just to probe the medium and see what the field looks like. So later on, we figured out the process, which was, by the way, is coined dielectrophoresis, similar to electrophoresis, except electrophoresis is with DC. This is with alternating electric field. Dielectrophoresis has this formula, meaning that electric current only applies a force to a charge particle, or DC, or static field. But alternating field applies forces not only to charged particles, to neutral particles, not only neutral non-polar particles, neutral non-polar. And that's the formula. As long as there's a difference between epsilon as the background, epsilon m, and epsilon as the object, particle p, there's a force applied. And that force is proportional to the gradient of h. Is the electric field higher here or lower here? In other words, when things start oscillating, the stuff that would oscillate like water would oscillate. The stuff that don't oscillate, get out of the way. That's why you create a flow, a multi-phase flow. That water would go somewhere, and the contaminant that's neutral, non-polar, like methane in that case, or bean apple, would go elsewhere. So we thought, okay, we figured out that this was the mechanism. And let me show you an example that should help you see that. This is the box. The cup is full of a dye, green dye that simulates bean apples. If you put it in there, bean apples are denser than water. So they diffuse out over a long time and sink down. You see the bottom is green. Now I applied a 65 megahertz field in there, and I say we take credit, graduate students do their works, we just advise them. So you see a little bit of dye at the center. The green goes up. It doesn't sink down. You see that? This is 65 megahertz, 10 watts of power. 10 watts is nothing, the bulb, yeah? Then 20 watts. You see more dye going up. You can probably see the green, hopefully in the image. And 30 watts, a lot more dye. You can extract the whole dye, and it goes to the surface, and you can extract it. The antenna is above the surface. In other words, I could have my magic wand above the surface and extract contaminants. So this is at 65 megahertz. Then we excited this at 75 megahertz. And again, students did, just myself as the PI and my co-PIs, just advised them. So at 75 megahertz, the dye stayed there for hours and hours and hours. Didn't even get out. This is only 3 watts of power. The minimum we could apply with our amplifier. Meaning that the application-wise, the first one was extraction. This one is that we could contain it there temporarily up until you find a solution for it, with a small amount of power. Now, why did this happen? We mapped the electric field experimentally just to validate our forward model, because measurement is just only at a couple of points. But when we validated our forward model, our simulation at a couple of points, we know that was a valid simulation. We had the electric field, and then we converted and this is at 65 megahertz. This is the electric field. And using this, if I find the dielectrophoretic force, that's the yellow arrow up. That means this 65 megahertz should push the contaminant up. This is what happens. At 75 megahertz, this is the electric field that we have simulated. This is the forward model results. And since it's a calculation, I could find the dielectrophoretic force off of that. The 2 yellow arrows won't push into the center. That means I can contain the contaminant. So that means we have a control. It's not just speeding up, or it's just random higher diffusion that we're doing. And obviously later on, we realized that the higher the power, the more dye was extracted. And at 0 power and 75, nothing, it's a flat red line. Nothing gets out. The horizontal axis is the power level, the vertical axis is the amount of dye that gets out. We also looked at the width of the finger that comes out of that. We talked today with Achilles about the finger formation. we could control finger formation, which is a good thing in manufacturing, a horrible thing in oil exploration, or a lot of, or MICP, or probably the colloidal silica type of remediation. When you try to inject things, sometimes you like fingering, sometimes you don't like fingering. So we could control it using electromagnetic waves. And we put the cup in different locations, and you see these two cups. When there's no electromagnetic waves, the contaminant sinks down. If there's electromagnetic wave here, it will move around. Those arrows is the force field. Wherever the force is, the dye goes. And two other cups, the dye goes up. Matter of fact, we change the frequency, and we could make the dye dance in there and change direction wherever we want. So in lab, this was proven. This works, not an issue. Now this is another one. Quickly, I go through that, and hopefully I get to the stuff that you like. This is an air spotting problem issue. As I told you, when you have a contaminated soil with VOCs, people inject air into soil and with groundwater, hoping that the contaminants would clean up, would evaporate. The problem is this: when I inject air into the soil, little channels form. I don't know if you see these little channels. And these little channels, the very first time that you crank up the pressure of air more and more and more, all of a sudden, the channels form. If I give you an analogy, if you have a cup that's empty, if I put a straw, blow in there, it's easy. But if I have water and I blow in there, I can't push the air in. And I got to push and push and push. And if the pressure is too high, bubbles form and come to the surface. I have no control. The same thing happens in soil. Channels form. And cleanup happens only around channels. We call them mass transfer zones. Nowhere else. What does the industry do? They realize this is an issue. They advertised air spotting, it wasn't working. So what they do is they run it for a month, they shut it off for 6 months, they hope they come back, turn it on again, and channels form elsewhere. They do a little, but not a lot, because you already moved soil particles and created preferential paths. So we thought, okay, we can move a contaminant that's neutral nonpolar, might be able to move air. Why not? So we ran an experiment very similar to that, and I don't want to get into the details of that, but first we tried to figure out how air spotting works. So we create several setups, fully saturated, halfway saturated, with a little bit of dry soil on top, with no dry soil on top. These are configurations 1, 2, 3 that we created. And then for these configurations, we ran a series of experiments. This is again another cavity. That loop antenna is on the left. The air pump is at the center. We pump air at the center. And first we try to see what air pressure does. One thing we realized is when you pump the air in there, let me show you an image that hopefully clarifies things. No, I don't have that image. So when you pump the air, I don't have the image yet. What happens is when you pump the air in there, it's going up, it's going because more of it. And if you look at the top view, there's a circle that's called, and the radius of that circle is called radius of influence. We thought we might be able to control this radius of influence. So this is zone of influence, and the radius is radius of influence. So first we wanted to see what air does, what the industry does, because the industry just pumped it up and didn't know what exactly happened. So what we did is we started the experiment, we crank up the pressure to a certain point, then air spotting starts. That pressure, I'll call it initiation pressure. And we wanted to see if that initiation pressure was high or low, would it have an impact? And after air spotting was running for a while, we would increase the pressure more and more and wanted to see if further pressure increase would change the zone of influence. Short of the story, we realized the initial pressure decides what the zone of influence is, how large it is. After the zones are formed, you could increase the pressure forever. You're not going to change it as much unless you move all the soil around with your pressure. And Then we said, let's see what electromagnetic waves do. And we predicted that electromagnetic waves would do the same thing. So these are the experiments, and this is the test to study the impact of initial pressure. And then we ran testing to study the impact of further increase in the pressure. We did the same thing with electromagnetic waves. We thought, okay, we apply electromagnetic waves before the system is turned on and see how it impacts it. And we apply electromagnetic waves, more electromagnetic waves after the air sparging is running, and see if there's any impact. And to tell you the truth, the ones on the left have an impact. The ones on the right, waves, pressure, doesn't matter. Channels are formed, channels are formed. Good luck, you can't change them. So, and this, in this figure, I have the radius of influence on the vertical axis, and I have the initial injection pressure on the horizontal axis. Configurations 1 and 2 are like that. You see the initial injection pressure, the higher the initial injection pressure, the larger the radius of. But obviously at some point it fluctuates. And configuration 1, which has configuration 2 that has some dry soil on top, confines it, so confines the soil, so the zone expands. That's why the blue line stays above the red line. And then further increase in the pressure on the horizontal axis is the further pressure increase after the system started. The vertical axis ROI, no change. No further increase in pressure increases the ROI. Now, we applied the same thing with electromagnetic waves, and these are the forward models, and these are the force fields. Look at, this is the top view of the field. And look at what happens later on in an image. The image on the right, on the left, is no electromagnetic wave. You see the top is the pipe, you get the air, and the circle, you see you have a pretty uniform, so that's half of the zone of influence, that's radius of influence. And on the right, I applied electromagnetic waves. And look at the shape of this zone of influence. It's deformed. Why did it deform? For that electric field, this is the dielectrophoretic force field. Look at the arrows. They push down and then stretch out. Basically, that circle should turn into a lips. A pair of lips like human lips. And you see that here. So we could design a field that changes the shape of the zone of influence, whatever way we want. And then we said, let's try different initial electromagnetic power to see if we could expand this zone of influence, like air did. And this is it. More initial electromagnetic field power before the system is turned on, that creates larger zone of influence. Vertical axis is radius of area of the zone of influence. Horizontal axis is the power, electromagnetic power. So we do have controls on the shape of the field, on the size of the field, and everything else, simply with that dielectrophoretic force. Then we said that, hey, two different things happen. 10 minutes, two different things happen. We don't know whether other things are happening. And we said, let's look at the hydraulic conductivity. If we're impacting the contaminant, if we're impacting the air, we might be impacting the water. First, we thought dielectrophoretic forces are working on the water too, so they should move in the opposite direction. And we thought, let's measure the hydraulic conductivity and see what happens. So here, this is the, by the way, this is just an explanation of liquefaction. As you know, the different ways to, when you have earthquake, excess water pressure goes up, and then soil particles lose touch, liquefaction happens, soil loses its shear strength. So the way people mitigate liquefaction is by either increasing the shear strength, compaction, dynamic compaction, other ways, or there are ways like IPS, induced partial saturation. People pump in air, the same air sparging method, to make the saturated soil unsaturated. And 5% unsaturation, 5% air content could improve, could mitigate liquefaction potential by 20-25%. So the research shows that. So basically, you're trying to IPS tries to decrease the pore water pressure increase by earthquake. So what we thought was, and later on I'll show you that we realized that the electromagnetic waves increase the hydraulic conductivity of granular soil like sand or silt or gravel, but they decrease hydraulic conductivity of clay. And we thought, hey, if we increase hydraulic conductivity in sand or silt, the excess pore water pressure would dissipate out faster. We can mitigate liquefaction. So that's the big picture of that research. So what we did is we said, let's figure out what happens to hydraulic conductivity first. And we ran some experiments, and I'll show you the setup. We looked at, we wanted to look at hydraulic conductivity change with electromagnetic waves, and we wanted to look at the pore water pressure change due to seismic shaking when electromagnetic waves exist there. And this is the two laboratory tests, Series 1 and Series 2, that I'll show you briefly. We tried it on glass feed, we tried it on, because it was cleaner, we could take images, and we tried it on natural sand as well. Again, we created a cavity, that box cubic that you see. We put a permeameter, the same ASTM standard, rigid wall permeameter, we put it in there. We put a monopole antenna in there, and we measured hydraulic conductivity, and then we turned on electromagnetic waves excitation in there, and at different power levels and frequencies, we looked at hydraulic conductivity to see what happened. So that was basically what we did in Series 1. Tried different frequencies from a couple of hundred megahertz to 700 megahertz and so on and so forth. And so basically, these are different tests: electromagnetic waves for hydraulic conductivity, constant head test, and falling head test for sand and clay. And then we looked at the excess pore water. Then we shook the device, and I'll show you some images and see whether we could mitigate liquefaction or not. Obviously, we had a shaking table that we would shake things. So Series 1, we put a permeameter in a cavity, we apply electromagnetic waves, we look at hydraulic conductivity. Series 2, we put a device that we could shake the soil, create simple shear, hopefully, and then measure excess pore water pressure rise, and then with or without electromagnetic waves, we control. So that's the whole theme of this. And this is the setup. There's a cavity outside, the same plexiglass covered with films. The two walls inside are flexible. The top is connected to an arm. The box sits on a shaking table and then shakes within the cavity. That's how I can, under the pore pressure transducer on the side, I can measure the rise of pore pressure as things are shaking as well. So this is the experimental setup we have. And again, we tried it at different electromagnetic powers. This is the result of hydraulic conductivity. The vertical axis is hydraulic conductivity. The horizontal axis is time. And we realized that the moment we turn on the electromagnetic waves, hydraulic conductivity gradually increases and plateaus at some point. In the previous experiment, we did not generate much heat. The temperature, unlike DC or AC that go up 40, 50, 100 degrees Celsius, this went up only 1.6 degrees Celsius. In all these experiments, we could pick the right frequency, so there's no heat generation. And we thought the only thing that could be happening is somehow the electromagnetic waves are changing the viscosity of the water. Basically, water is like the positives of one molecule are attracted to the negatives of the other molecule randomly. That's why it's a little bit, when you apply electromagnetic waves, you reorient them with the field. Maybe we're reducing we're still trying to understand this. Maybe we're reducing viscosity, that's why we're increasing hydraulic conductivity. And not only the peak relates to electromagnetic powers, the slope relates to electromagnetic powers as well. And obviously, again, like before, the constant head test is a uniform flow. So that's why that simple formula exists, that you know what the discharge is, you measure it, you know what the hydraulic conductivity is. When you have a field that's non-uniform, then your hydraulic conductivity would be non-uniform. So we have a forward model for electric field, a forward model created for CPEX, and we assume that K tensor, the full tensor of K, turns into K prime. And that K prime, I'll show you the formula, is different. So we created a forward model for seepage. We validated in the lab. We know it works with no electromagnetic waves. And then, and this is basically the hydraulic head pattern within the soil using our model. And this is when you have electromagnetic waves. We assume the relation between K prime, electromagnetically stimulated hydraulic conductivity, and K was this. And then we calculated the K prime with an alpha that we didn't know what, it was just an assumption. We stimulated the flow, we figured out what the discharge was compared to the experiment, ran that optimization, minimized that cost function, and figured out what that formula was. So we developed the governing equation of how hydraulic conductivity changes with electromagnetic power. And we have that for sand. We were so happy, we said, hey, we got it. And this is, by the way, as the power goes up on the horizontal axis, the hydraulic conductivity ultimate value goes up on the vertical axis. In this case, 25% for sand, and it was smaller for glass bead. So silt helps with that process. And this is the pattern of how hydraulic conductivity changes. And these are the maximum values for different frequencies. You could see 15%, 26%, and so on. Oh, by the way, this is clay. I'll show you this figure. This is clay. We were so happy that we know this governing equation, how hydraulic conductivity increases. Then we looked at clay. The horizontal axis is time, vertical axis is hydraulic conductivity. The blue line is no power. The moment you apply 30 watts of power, hydraulic conductivity goes down almost by 98%. And then there's a little rebound. And then you shut it off, it goes up and rebounds higher. And then the last is done. You turn on a 20 watt with a 20 watt, it drops down again. And then you shut it off, goes back up, and normal natural angle, and then you turn it at 10 watts, goes up. So basically, clay hydraulic conductivity goes down with electromagnetic waves. And we have a theory, but still trying to validate that. And the theory is, because of the alternative field, your double diffuse layer is expanding and contracting, expanding and contracting. And that dynamic is increasing, decreasing the hydraulic conductivity, decreasing the flow, making the soil less permeable. We think that's related to double diffuse layer, which is not dominant in sand. So, and this is how more power decreases hydraulic conductivity of clay at different powers. That's pretty much linear as well. I think my time is almost up. And this is the pressure that we study. Again, I have to skip these, but it shows with different shaking and different power how we control that. The problem is the integration, but we got to modify the setup, because with the setup we have the pressure dissipating out, but no way of shaking, so we couldn't mitigate the contraction to the level we want. But we still understand, we're trying to understand. As I said, we have a patent pending, so I can't discuss this too much. And this is pretty much all I had. Now, as I said, before I open this floor, other projects that we did, this is electric stimulation of microbial activities. We realized electromagnetic waves can stimulate or stop biodegradation or microbial activities. You could use it for biodegradation, remediation stimulation. We try to apply it to beer breweries as well, to speed up brewery as well. So you could control that. There's so many different things happen. Here is some other studies we have for the soil particles on Mars, because they're charged and they cover all the astronaut suits and solar panels. So we try to study how the charged soil particles work or behave in vacuum on Mars and Moon. That's a NASA project. The previous ones are all NSF projects. And other projects, we developed sensors that would mix the regular measurements by geophysicists or other sensors, but sometimes the contamination level is so low that physically you cannot detect it. But we mixed it with the pattern of the design, that dielectrophoric forces will push all the contaminants to one side. So you artificially rise the concentration and detect the This was for medical purposes that we tried to develop this. And for water quality purposes, this works. These are all result. Tunnel detection across the Mexican border. We use geophysics for that purpose. And moving, we try to detect moving humans in there and so on and so forth. I don't want to get into the details of that. This is another project for the Army. If I told you more, I would have to kill you, and I'm kidding. So we tried to develop a device that fully characterizes soil in a window of 5 to 10 minutes and lightweight so it could be deployed quickly for the Army. This is structural research that I do on power transformers and their vulnerabilities and the bushing failure and so on and so forth. So we came up with a result that basically IEEE adopted, and they realized the previous standard was that ASC and IEEE used were wrong in terms of the amplification factor. So this is what we did. Again, the structural work and shaking table test on these bushings. And you could see why they failed, because there's a big branch with the big side and the bushings on top of the transformers and the transformer. We try to work on other research, and this is an energy geotechnics to try to use soil as a source or sink of heat to store energy, which is and the simulation and experiments and so on and so forth. And I don't want to get into the details of that. And by the way, we realized that if you have piles, drive them in clay, obviously there's a pile setup phenomenon. You got to wait 1,000 days for the capacity to build up. If you turn on your HVAC system that's connected to the piles, because you put the circulation into the piles to use the ground as a source of heat or sink of heat, then the capacity drops. So you got to be careful with that. So the impact of energy piles on was another thing. So these are my co-PIs. Dr. Jim Browning and Dr. Elisa Barney Smith. A lot of graduate students, I had their name somewhere else, but I'll stop right here. I think I went beyond my time a little bit. So if there's any questions, I'll try to